Auxiliary problem is a problem which we consider not for its own sake, but because we hope that its consideration may help us to solve another problem. Yes. Our original problem. The original problem is the end we wish to attain. The auxiliary problem a means by which we try to attain our end. An insect tries to escape through the window pane, tries the same again and again, yes, and does not try the next window which is open and the through which it came into the room. Yes. A man is able or at least should be able to act more intelligently. Yes. Human superiority consists in the going around an obstacle and that cannot be overcome directly in devising a suitable auxiliary problem when the original problem appears insoluble. Yes. To devise an auxiliary problem is an important operation of the mind. To raise a clear-cut new problem subservient to another problem, to conceive distinctly as an end what it means to another end, is a refined achievement of their intelligence. It is an important task to learn or to teach how to handle auxiliary problems intelligently. Yes. 1. Example. Find x satisfying the equation x to the fourth power minus 13x squared plus 36 equals 0. If we observe that x to the fourth power equal bracket x square bracket square, we may see the advantage of introducing a y equal x square. We obtain now a new problem. Find y satisfying the equation y squared minus 13y plus 36 equals 0. The new problem is an auxiliary problem. We intend to use it as a means of solving our original problem. The unknown of our auxiliary problem, y, is appropriately called auxiliary unknown. Yes. 2. Example. Find the diagonal of the rectangular parallel pipe being given the length of the three edges drawn from the same corner. Trying to solve this problem, we may be led by analogy to another problem. Find the diagonal of a rectangular parallelogram being given the length of the two sides drawn from the same vertex. The new problem is an auxiliary problem. We consider it because we hope to derive some profit for the original problem from its consideration. Yes. 3. Profit. The profit that we derive from the consideration of the auxiliary problem may be of various kinds. We may use the result of auxiliary problem. Thus, in example 1, having found by the solving the quadratic equation for y, that is y is equal to 4 or to 9, we infer that x squared equals 4 or x squared equals 9 and derive hence all possible values of the x. Yes. In other cases, we may use the method of the auxiliary problem. Thus, in example 2, the auxiliary problem is a problem of plane geometry. It is analogous to, but simpler than, the original problem, which is a problem of solid geometry. Yes. It is responsible to introduce an auxiliary problem of this kind in the hope that it will be instructive, that it will give us opportunity to familiarize ourselves with a certain methods, operations, or tools which we may use afterwards for our original problem. Yes. In example 2, the choice of the auxiliary problem is rather lucky. Examining it closely, we find that we can use both its method and its results. Yes. 4. Risk. We take away from the original problem the time and the effort that we devote to the auxiliary problems. If our investigation of the auxiliary problem fails, the time and effort we devoted to it may be lost. Therefore, we should exercise our judgment in choosing an auxiliary problem. We may have various good reasons for one choice. The auxiliary problem may appear more accessible than the original problem, or it may appear instructive. Or it may have some sort of the aesthetic appeal. Sometimes the only advantages of the auxiliary problem is that it is new and offer unexplored possibilities. We choose it because we are tired of the original problem. All approaches to which seems to be exhausted. 5. How to find the one. The discovery of the solution of the proposed problem often depends on the discovery of a suitable auxiliary problem. Unhappily, there is no infallible method of discovering suitable auxiliary problem, as there is no infallible method of discovering the solution. There are, however, the questions and suggestions which are frequently helpful as look at the unknown. We often look at unknown. We are often led to useful auxiliary problem by variation of the problem. Yes. 6. Equivalent problems. Two problems are equivalent if the solution of each involves the solution of the other. Thus, in our example 1, the original problem and the auxiliary problem are equivalent. Consider the following theorems. A. In any equilateral triangle, each angle is equal to 60 degrees. B. In any equiangular triangle, each angle is equal to 60 degrees. There are two theorems are not identical. They contain different notions. One is concerned with the equality of their sides, the other with equality of the angles of their triangle. But each theorem follows from the other. Therefore, the problem to prove A is equivalent to the problem to prove B. Wow! If we are required to prove A, there is a certain advantages in introducing as an auxiliary problem the problem to prove B. Yes! The theorem B is a little easier to prove than A, and what is more important, we may foresee that B is easier than A. We may judge so. We may find plausible from the outset that B is easier than A. In fact, the theorem B, concerned only with angles, is more homogeneous than the theorem A, which is concerned with both angles and sides. Yes! The passage from the original problem to the auxiliary problem is called convertible reduction. So you can convert, right? Or bilateral reduction, or equivalent reduction. If these two problems, the original and auxiliary, are equivalent, thus the reduction of A to B is convertible, and so is a reduction in the example 1. Convertible reduction reductions are, in a certain respect, more important and more desirable than other ways to introduce auxiliary problems. Yes, but auxiliary problems which are not equivalent to the original problem may also be very useful. Take example 2. 7. Chains of equivalent auxiliary problems are frequent in mathematical reasoning. Again, chains of the equivalent auxiliary problems are frequent in mathematical reasoning. Yes, we are required to solve a problem A. We cannot see the solution, but we may find that A is equivalent to another problem B. Considering B, we may run into a third problem C equivalent to B. Proceeding in the same way, we reduce C to D and so on, until we come upon the last problem L, whose solution is known or immediate. Each problem being equivalent to the preceding, the last problem L must be equivalent to our original problem A. Thus, we are able to infer the solution of the original problem A from the problem L, which we attained as a last link in a chain of the auxiliary problems. Yes! Wow, so cool, so cool. Chains of the problem of this kind were noticed by the Greek mathematicians, as we may see from the important passage of the Paps. For an illustration, let us reconsider our example 1. Let us call A the condition imposed upon the unknown x. X to the fourth power minus 13x squared plus 36 equals 0. One way of solving this problem is to transform the proposed condition into another condition which we shall call V. Yes! Bracket 2x squared bracket 2x squared of square, okay, minus 2 bracket 2x squared bracket 13, so times 13 plus 144 equals 0. Observe that the condition A and B are different. They are only slightly different if you wish to say so. They are certainly equivalent, as you may easily convince yourself, but they are definitely not identical. The passage from A to B is not only correct, but has a clear-cut purpose, obvious to anybody who is familiar with the solution of the quadratic equations. Working further in the same direction, we transform the condition B into still another condition C. Yes! C bracket 2x squared and bracket square minus 2 times bracket 2x squared times 13 plus 169 equal 25. Proceeding in the same way, we obtain D bracket 2x squared minus 13 bracket square equal 25. E 2x squared minus 13 equal plus minus 5. F x squared equal 13 plus minus 5 over 2 divided by 2. G x equal plus minus root 13 plus minus 5 divided by 2. H x equal 3 or minus 3 or 2 or minus 2. You! So cool, so cool. Wow. Each reduction that we made was convertible. Thus, the last condition H is equivalent to the first condition A, so that 3 minus 3, 2 minus 2 are all possible solutions of our original equations. Yes! In the foregoing, we derived from an original condition A, a sequence of condition B, C, D, each of which was equivalent to the foregoing. This point deserves the greatest care. Yes, equivalent conditions are satisfied by the same objects. Therefore, if we pass from the preceding condition to a new condition equivalent to it, we have the same solutions. Yes. But if we pass from a proposed condition to a narrower one, we lose solutions. Yes. And if we pass to the wider one, we admit improper, adventitious solutions which have nothing to do with the proposed problem. Yes. If in a series of successive reductions, we pass to the narrower and then again to wider condition, we may lose track of the original problem completely. In order to avoid this danger, we must check carefully the nature of each newly introduced condition. Yes. In order to avoid this danger, we must check carefully the nature of each newly introduced condition. Is it equivalent to the original condition? This question is still more important when we do not deal with single equations as here, but with a system of equations, or when the condition is not expressed by the equation, as, for instance, in problems of the geometric constructions. 8. Unilateral reduction. We have two problems, and A and B both unsolved. If we could solve A, we could hence derive the full solution of B, but not conversely. If we could solve B, we would obtain possibly some information about A, but we would not know how to derive the full solution of A from that of the B. In such case, more is achieved by the solution of A than by the solution of B. Let us call A the more ambitious and B the less ambitious of the two problems. If from a proposed problem we pass either to a more ambitious or to a less ambitious auxiliary problem, we call the step unilateral reduction. There are two kinds of the unilateral reduction, and both are in the same way, in some way or other, more risky than the bilateral or convertible reduction. Our example 2 shows a unilateral reduction to a less ambitious problem. In fact, if we could solve the original problem concerned with a parallel pipe whose length, width, and height are ABC respectively, we could move on to the auxiliary problem putting C equals 0 and obtaining a parallelogram C equals 0 or I think it's 0 and obtaining a parallelogram with a length A and width B. For another example of the unilateral reduction to a less ambitious problem, or C, specialization 3 to 4, 5. Yeah. These examples shows that with some luck, we may be able to use a less ambitious auxiliary problem as a stepping stone, combining the solution of the auxiliary problem with some appropriate supplementary remark to obtain the solution of the original problem. Unilateral reduction to a more ambitious problem may also be successful. In fact, the more ambitious problem may be more accessible. This is inventor's paradox.